For this part of the video, I wrote in the comments the information we are going to need in this section. So let's start with the car data type. The car data type can be interpreted in two ways. Um, the most often is the most frequent use is that of written characters, whether it is letters or special characters, numbers. However, they can store small numbers. I hope that you saw one video in which I explained the uh, type of data in binary that can be signed or unsigned. That is, it can take just positive values or both positive and negative values. So when you specify nothing else than the car data type, it will interpret a range of values from a part negative values and another part of um, positive values. So let's start first by creating this variable car type. So we type car, then we give it a name, let's say yen, and then you give it a value that must be within this range, otherwise it will throw error. So let's say for instance uh, the last possible value 127, then end by semicolon, and then what's the format specifier? It is %c, but since we are using this char variable as a numeric value, so we're going to specify %d for numeric values, okay? Otherwise it will read this as a equivalent character. So first of all we want to use it as a numeric values, okay? So then comma, and then you pass the name of the value that contains that numeric value. So yen contains this value. Okay, it runs okay, says the same value here, but see what happens when we surpass these boundaries. So let's give it this larger value beyond its range of 128, surpassing the value, the limit of 127. Here you start to notice errors. It doesn't show the value of 128, but minus 128. So that's how you know that it didn't write the right value. So it means that you are doing something wrong. And in this case, is that you went beyond the limits of this range. Same if we go beyond the negative boundary, a number more negative than this 128, well, minus 129. Let's see what happens. As you can see, it throws some kind of error in the message and also displays a wrong number, 127. So that's how you know it's wrong. So don't surpass these values in the different um, type of variables, different data types, okay? Be aware of the ranges. Now we're going to use this car, uh, giving it an actual character value. So when you write messages with several characters, you always do use double quotations or for these format specifiers. But whenever you write a single character, you must place it within single quotations. So let's say for instance a letter Y, and since we are changing this to be a character, not a number, we are going to change the format specifier here for its original expression, which is percentage %c. So it's going to be read as a character. So it should read Y, the Y letter. As you can see, it is okay. You can use also some special characters, and it will display the same. However, if you interpret this data in other format and you say, okay, it is a numeric value, you will throw a equivalent numeric value. So be aware that you are using the format specifier according to the type of data that you want to read. If you want to read this a card value as a character, you use %c, and if you want to read it as a small integer within this range, well, you use this %d. To wrap it up with this card data type, we can consider that, okay, you may say, what's the use of this card data type being interpreted as a special characters, letters, or numbers, that is as written symbols, and also as these small ranges for integers. So bear in mind that when you are using this for small integers, you can use this as a space-saving strategy. That is, for instance, let's say that you are counting up to 50 every time, so you don't need any greater amount than these ones. You can get the job done by storing that numeric data in this card type, and you would only take 1 byte of memory rather than using one of these integer or other data types that actually take longer sizes. So bear that in mind, that could be a use. Alright, now let's review this end data type, that is integer. So let's start by taking into account we can't surpass these boundaries, these ranges of the numeric values that it can store. Just like before, remember that if nothing is specified before this end, when you create that variable, it will assume that it is signed. That is, you will take a range of negative values and a range of positive values. So let's start by creating the data, that variable, sorry. So let's type int, give it a name of yen, for instance. And now we're going to use this one as a limit. Now end by semicolon, and then remove these commas, just the bar digits. What do we need now? Okay, apply this format specifier of %d. Remember that %d will imply that, okay, this is a numeric value, but it can have a negative number or a positive number within this range. Okay, so D stands for a signed numeric amount. It can be negative or positive within this range. So now comma, and then pass the name of the variable that contains that data of that type. Okay, now let's run it. It's okay as expected, but what happens if we cross that boundary? Let's increment this by a unit and see what happens. It will throw a wrong number. Have a look here. It was written as negative number, so that's how you know you're doing something wrong. What we are going to do now? Okay, now let's use the same trick again. Let's write the attribute unsigned. So remember that it will enlarge this range. So all this portion, all this part of the range that were negative numbers are going to be merged with these positive numbers. So it will start again, just like in unsigned car, from 0 up to the maximum positive value. So now let's do okay, let me see. Okay, let's do it and see what happens now that it is unsigned. It displays the same wrong number. What happens here? just as I was telling you, this percentage %d is a format specifier that specifies that it is a signed amount. I mean, it can take both negative and positive values. But what happens? It stays in this range. No matter that I converted this amount to an unsigned data, but here in printf, which depends on this format specifiers to do its job, it's taking this as a number that can take also a range of negative numbers. So what the main mistake here is that I have to correct this format specifier, and it's going to be to match the same type of data we have here, which is unsigned. So it has no negative numbers. However, this percentage %d takes both negative and positive. So this has to be replaced by this letter, which means unsigned. And this format specifier will now match the same data type here and will allow us to show the same this amount without any errors. Well, I'll be explaining some other details on data types, but for now, let's just leave it this way and continue to the next type. Okay, now let's review the float data type. This data type is used to store values of real numbers, that is numbers with integer part and fractional part. So the format specifier is percentage %f. This is the range that it has, and it will provide numbers with 6 decimal digits. So let's start by creating a float data type. Let's give it a name, and then let's store a value inside. So let's start the value of 3/5. As you can see, the value of 3/5 is 0.6. So let's see what happens. Now complete here the format specifier in printf, comma, and the name of the variable. And now let's print it. As you can see, it is a wrong result because we forgot to use the right notations for float variables. Since we want this to take any fractional part, fractional digit, and be printed here, we have to use the same notation. We have to write this any of these operands in its with decimal digits. So it should be 3.0, just one of the operands. Or if you want, it may be both. However, at least one of the operands must be in this notation to get the result. So now we have the right result. Remember, it has 6 decimal digits here. And now I'll show you something. In this format specifier between the percentage and the f, you can specify how many digits you want to be displayed here, how many decimal digits. And you can use it by either placing point, which represents the digital point, and how many digits do you want in decimals. You can use, for instance, let's say 2, just 2 the decimal digits. It's okay, right? It worked. Also, you can place a number here first that will tell the program how many places you want to occupy to write this number, this result that you are giving in this variable. So it tells the minimum amount of spaces or places here that you are going to write, the minimum amount, bear in mind. So let's say that I want to use just two positions here. As you can see here, it will this number represents the all of the numbers maximum minimum values that would be minimum positions or characters that will be written, including the decimal point. That means, for instance, let's count how many do we have here. We have 1, 2 decimal points, 3 with those decimal point, and 4. We have a total of 4. But we wrote that we wanted to be at least 2. That means that it can be 2 at least, but if the program considers that it needs more spaces, it will use more spaces. So let's see what happens. As you can see, it's written appropriately because this number does not constrain the program to use just that few spaces, but actually uh, depending how many the program needs, they will be used here. So it will obey mainly how many decimal digits you want. However, you can specify what happens if this number is greater. Let's see if I say, okay, I want seven places to be written. So what happens then? Here we have 1, 2, 3, and 4. So we are still need 3 more spaces. Let's see what happens. It will fill with the remaining places, that is the 3 more spaces necessary to write a total amount of 7 with blank spaces. Okay, now let's store a different number. So let's use this one. I'll take this one with fewer decimal digits. So let's run it and see what happens. Uh, okay, remember that you can leave this with just the decimal point and the number of decimal digits that you want. You don't want to write this first number if you don't want to. So what do we have here? As you can see, I asked for 2 decimal digits. So what did happen? Um, in this decimal digits are 896 were rounded to 90. That is like 900. Okay, so it was rounded to match this amount of decimal digits, and the rest is okay. All right. What if I want to use the 3 decimal digits we will have? So this is okay. So now let's see what happens here. I guess we are going to have a little problem. I'll show you what I mean. Let's now store this value here, and let's not specify an amount of digits that we want, so it will be by default 6 decimal digits, and here we have 6 decimal digits. Pay attention to what the number is. Okay, let's run it, and as you can see it says 123 point, and this number is not the same. This is one decimal digit less than this one, and I guess it is because maybe we have surpassed this the range of this value. So we're going to the next, which is a double data type, and we'll see that it gets resolved. Remember, as I told you, when you surpass any of these boundaries, different ranges for every data type, you'll start notice some different numbers being written on the screen. Uh, so what we're going to do now, the next data type is double, which serves also for real numbers. This is the format specifier. As you can see, it occupies more bytes than the previous one. It is called double precision decimal numbers. So okay, what we are going to do is use this next data type and see if it gets resolved and we get the right number here. So remember, first of all, we have to change the data type. Now it's going to be double. Okay. and also the data, the format specifier, which is going to be LF. So it is like a long float or something, okay? Remember, LF, and okay, let's see what happens. Let's hit run. What's the mistake? Oh, I wrote this number of double wrong. So double. Okay, let's run it again. And here we have uh, every decimal digit, digit by digit. 8, 9, 6, 7, 4, 5. It is okay. All right. So this double data type has a much longer, much bigger range than the previous float data type. Okay, so I think that was the problem with the ANOVA. So bear that in mind. Whenever it does not show it exactly the same number, it is because maybe you are beyond the boundaries, the ranges of the data type. However, if you take a look here, you will find that it says that it can provide up 15 decimal digits. So now let's use that trick that we learned previously of the number of digits that we want to display in the format. Remember, between the percentage and the letters of the format specifier, okay? So remember that we don't have to write the initial number, so we can leave it without this first number and just place the point and the number of decimals that we want to display. Uh, so let's say, for instance, here we have 6 decimal digits, so let's copy and make it 12 digits, 6 plus 6, and specify here that we want to uh, write 12 decimal digits and see if we get that result. Let's run it, and here you have 896,745 and 896,745. Okay, it is okay. So as you can see, it didn't by default shows that amount of decimal digits, but it was stuck in just the default value of just 6 decimal digits, so you can use this trick. But remember that it must match the the same characteristics of this type that you just wrote here. I mean, I'm specifying that this is a LF for double, and I am passing this value of an actual double. Okay, so it must match the format specifier and the type of data. Okay, because if I do the same but with the float that can provide just 6 decimal digits, it will be an error, so bear that in mind.